So I'll read out what's written there, but I'm going to talk a little bit more once we get to the mathematical stuff. Once we've identified a linear association between two numerical variables, we can fit a linear model to the data and find the equation of the line. We can then use this model to make future predictions. So chapter 1 was all about building a scatter plot and testing the association between the variables. And you'll get a correlation coefficient of 0.1, in which case there's no association or barely any association. And in that case, you're probably not going to do a linear model. You might get a correlation coefficient of 0.95, in which case there's a strong association, and a linear model will be appropriate. But a linear model won't perfectly fit the data, but it could be appropriate even if it doesn't perfectly fit the data and help you to do something that we call extrapolating or predicting or forecasting, which will be the term used when we get to time series as well. So this is called a linear regression. And you may have, so I'm going to have to move off this page and back. It's funny. You may have done or dealt with regressions before. It's really common in any situation where you're collecting data. So if you're doing science, you may have used regression before, but you'll just determine a regression straight off Excel or Desmos or whatever you want to. Your graphics calculator, if you've got one, for example, does that type of thing. You can also get your regression off the scientific calculator, and I'll show you that a little bit later this lesson as well. It's a linear regression, so it is a linear function. Y equals mx plus c is the standard form of a linear function, but your calculator and Excel will have it in this form, y equals a plus bx. Nothing to be scared of. The gradient is m here, the gradient is now just b. It does have a contextual purpose. The c value is your y-intercept, the a value is now your y-intercept. They've just been swapped, and m and c have turned into a and b. That's just the way it is. So you'll need to get used to that and how to use that form. So I'm going to go down now and talk about the abstract. And so you're going to have to just take a couple of deep breaths, prepare yourself for the abstract. I'm going to show you where this linear regression comes from and what it means. So here it is. There's a funky looking diagram. What a linear regression does, and this is why Excel's so good at calculating it, and this is why a calculation that we do for this is going to end up looking a little bit complex. A linear regression determines the straight line such that it minimizes these d value lengths. So the d values are your vertical distance from each data point to the line, and you can see if I took this line, imagine I can pinch the screen, and I moved it up a little bit, the line would get closer to D2 and D3, and maybe even a little bit closer to D5, but it would move further away from D1. So our calculation will give an optimized linear function such that the total distances here, if you add them all together, is minimized. If I had the line up here somewhere, obviously that would be really bad. So your line should be somewhere in between the data points. Usually you'll have about an even number of data points above or below your line, but it will minimize those. That's the abstract though. You don't really have to worry about that because you'll never have to draw this and start thinking about those distances. I'm going to give you the formula that create that minimized line. I'll give you the formula that Excel uses when it does it. But for now, that's the background. So if you are thinking about what a regression line means, that's what it means. That understanding there might be a really handy reference point in the PSMT. If you're discussing why you created a regression line, you might come back to talking about this. So it wouldn't really come up in an exam, this understanding, but PSMT it might be handy. So this is the mathematical side of things. So least squares regression is minimizing the square distances. We use square distances instead of just distances because that's negative distance, that's a negative distance. If we add all those together, we get 0. So we square them first, just like we do with standard deviation. That makes them all positive, and then we're minimizing that positive value. Same as those, yeah, okay, so there's some assumptions there. And I've talked about why we square them instead of just using the raw score because of the way averages work, they would equal 0. So here's the actual mathematics you'll need to be able to do. That's it right there. That's pretty much a summary. So if you wanted to write down something important from today, this would probably be it. So I'll talk about this briefly. And I've actually pinned up your formula sheets over here, and I can't remember the time of the formula sheet. I feel like it is. And so yours is here. Elements of it are, but not the whole thing. So you'll need to know how to do this, and you'll need to probably remember most of it. So to get your least squares regression in the form of y equals a plus bx, y-intercept slope. So it's in that form, but just flipped around a bit. Your b is equal to the correlation coefficient r times by the standard sample deviation of y, sy, we've used these both before, divided by sx. So that's this formula here in blue. And a is equal to the mean y value minus b, which you've already calculated, times the mean x value. So you will need to know the following things: r, sy, sx, x bar, and y bar. And then you will use those things to determine, first of all, your b, and then your a value. Has to be b then a, because the a value relies on the b value. But you are dealing with, and this is unavoidable pretty much, unless you get a really simple question where they say, some of the questions would say r equals this, x bar equals this, y bar equals this, so you might get some simple questions. If you're dealing with a question that's in any variable, i.e. your PSMT that you're going to get next week, your r value is going to be some horrible decimal. Your sy and sx are probably going to be some horrible decimal. X bar and y bar, you might get lucky, but they're probably going to be some horrible decimal. Therefore, your b and a are probably going to be something horrible in decimal. So just be prepared for that, and you're going to be dealing with that. So we go back to that thing we talked about last week again. When you're putting values into here, try and maintain a level of accuracy as you go through. And my recommendation is, if you want an accurate 2 decimal places at the end of a question, work with 4 decimal places during the question. If you work with 4 decimal places, that's 100 times better, because we're working base 10, 10 squared is 100. And so the chances of being out of, even by a decimal, at the end are pretty low if you work with 4 and then go down to 2 at the end. Are there any questions on this? Here's a little note which I'd like to highlight. X has to be the explanatory variable. Remember, we always plot independent and dependent. We plot explanatory and response variable. Your X has to be the explanatory variable. So you should always start a question by considering that, unless you're given a graph where it's obvious or you're told. Consider and make sure that you're using the thing that explains the other variable as your X value. And I'm going to do an example with you now. And I know some people are copying stuff down, but I'm going to move to there. The examples here, and I'll go through and calculate this, but I might just give you another minute or two to copy down. So let's have a look at this example. And if you haven't copied everything down, I'm sorry, you might just have to shoot back there on the OneNote a little bit later. So in this example, the context is given as the height and weight of 11 people, which have been recorded. I'll make the note very quickly. 11 people is not very many. It does not provide solid statistics. Usually you're looking for 20 or more. And depending on what the population is, if we're talking about statistics for the whole of Australia, we would like our sample to be even bigger again. So 11 is not many, but we'll move forward with the question. First of all, they've defined X and Y. Are we happy with that order for explanatory response variable? Does anybody have any comments on that? It's all good. So the point here is we need to think, does X explain Y? Now, with something like body measurements, often we've got to be careful that there is actually an explanatory and a response variable. But in this case, I asked myself the question, if I grew taller, and I'm well beyond that otherwise, but if I grew taller, I would get heavier. But if I go away now and just eat bad food and put on weight, that won't make me taller. So think about it like that. If I grow taller, that will affect my weight. But if I put on weight, that will not affect my height. So therefore, I'm happy that height explains weight, but weight doesn't explain height. Is that all right with everybody? So it's a really simple way of doing it, and just thinking about that explanation. Think, if I change this one, would that affect the second one? If it would, then you've got your explanatory response variable sorted. So we're happy with this being weight No, I've got that wrong already. Height and weight there. And I want to determine my, I want to calculate the value of the slope and the intercept to two significant figures. So we'll get to the significant figures in a minute. So first of all, the slope is our B value. And remember, we have to calculate B before we calculate A. So our slope equals B. And according to the formula above, that's equal to RSY over SX. And so I put that in my calculator. R times SY, which is 0.8502 times SY, which is 7.594 over SX, which is 7.444. I'm not worried about rounding in this case. They're just the values that have been given to me, so I've had no effect on that. It's outside of my control. 8502 times 7.594 divided by 7.444. This is equal to 0.8673 dot. The question says to two significant figures. So what I do then is I come from the top end and I count from the first significant figure. So what's my first significant figure here? Keep in mind, significant figures are non-zero figures that aren't, so some zeros are important. So for example, if I have 0.102, that zero is important because it's between two non-zero digits. So it represents a place value. But in this case, that zero is not important. My first significant figure is 8. My second significant figure is 6. I go to the third figure and decide if it rounds up or down. It rounds up. So two significant figures is 0.87. So you need to make sure you know and can use significant figures. 87. That's my slope. But I need to find my A value now as well, my intercept. And I'm going to use the unrounded version of B. I've got to make B. So my intercept, which equals A, is equal to Y bar. I'll have to remind myself, is it minus? Yep. Minus B X bar. And so in this case, that's equal to 65.45 minus 0.86733 times by X bar, which is 173.3. And that's equal to, so I've got this is as my answer. My B value is my answer to the previous question. So I'm going to use the answer key. 65.45 minus answer times 173.3, and that gives me negative 84.8586, and on two significant figures again. The first significant figure is the 8 at the top here. The second one is the 4. Does the third significant figure round up or down? It rounds up, so the 4 becomes a 5, and this is approximately equal to negative 85 to two significant figures. Now, you may be asked to describe a set or talk about what these actually mean. So in this case, the intercept here, which is the y-intercept, the negative 85, that means that if x is 0, x is the height, it tells you or gives you some indication of the starting weight. Y bar, I'm assuming, should be kilograms, 65.45 kilograms. Anyway, if my height was 0, this model suggests that my weight would be negative 85. That's what the intercept means in context. Obviously, it's irrelevant. There's going to be what we call a restricted domain. There's going to be only a certain part of this graph and this model that actually works. Once you get past a height of 250 centimeters, it's irrelevant. Once you get below a height of 50 or 100 centimeters, it's irrelevant, but it works in between. So we're happy with that. And that's called extrapolation or interpolation. Interpolation is when you're predicting inside the data. Extrapolation is when you're predicting outside the data. Interpolation is good and works well, and that's what we build this for. Extrapolation works well, but only if you go a little bit outside the data. below or above. The slope, 0.87, suggests to me that as I grow a centimetre, I go up 0.87 kilograms in weight. That's what the slope means. So if I think about this, it's going to have a positive correlation. As I get higher, which is the x-axis, my weight goes up. So I'm expecting to have a positive slope, but I could have a negative or positive intercept. Are there any questions on that? For the sake of the video, I'm going to just quickly do this. If anybody is watching the video, they can pause now, have a read of this. That's how you do it in your calculator. If anybody is watching the video, they can pause now, have a look at this. That's how you do it in Excel. Obviously, it's on the OneNote as well if you've got access to that. And that's the end of it. But I'm going to stop the video, and we're going